Welcome guys. Today we are going to see about the most stones removed the same row or column question. Okay, let's see the question. On a 2D plane, we have n stones or some integer coordinates. Each coordinate point may have at most one stone. Stone can be removed if it shares either the same row or the same column as another stone that has not been removed. Okay, we will get an array of coordinates where the stones are at, and we have to find the largest possible number of stones that can be removed, right? Okay, uh, um, for this example, let's think about it like this. Let's say we have some pattern. Let's say this part is the grid, so that it will be easy for us. If let's say this is the grid, and excess would be the places where the stones are at. If we give some random places where it is, if this was the case, what can we do? We can remove this first one because there is something in it, so and we can't do anything here. Okay, so we can only remove it if they are in the same row or column. Okay, what we can do basically here would be beginning, we can make a graph of or let's assume this each stone to be a node, and we can make a graph where the edge represents whether they share a same row or column. Okay, so if we have such a graph, then what are we looking at? We are looking at the ones which can be removed, so one which has at least one edge. While removing edges, what? Okay, so it seems something like a topological sort, right? Okay, but in topological sort, we can do remove. We are removing each element, which is having the odd number, so that we don't miss anything. Something like that. Okay. Okay. I think this question is we if there is any connected component, let's say one fully, it doesn't need to be fully connected component. There are some nodes with which all the connections are there. Then we can say that we can remove each and every element from that uh, component except one, right? Let's say we have 10 nodes in some graph. We will remove each and every one in that in the topological sort. We are having certain order. We don't need to follow that order at all, right? If you follow that order, you can understand it better. It just topological sort just says that if there is an edge, we are removing each and every one. But uh, in the topological sort, we remove the last element also. But here we can't remove it because it doesn't have any edge to any other element, right? So it means that we have to find, let's say, we found a connected component. We have to find number of nodes in it minus one. That would be the number of nodes that we can remove in that component. So for that, what we can do is we can we have to form an adjacency list and visited array. Okay, now we will see the solution. First, we will initialize the required variables and ij for iterations, and we will need to return some answers. So these are the things. We will need to form an uh, adjacency list and visited array. So we'll keep visit and we will need an adjacency list. So in adjn. Okay, so 0 I less than I plus plus. j is equal to 0, j less than I, j plus plus. I'm not taking j equal to I because I don't want any self loops in my final graph. That's my thinking in that region. Okay, if stones I0 is equal to stones J0, or like what we are basically saying is if their rows are same or columns are same, if at least one of these two are same, then what we do is we have to push J into I, and the same goes for J also. Since if A and B are connected, B and A are also connected in this context. It's basically an undirected graph here. Okay, we will also need to initialize the visit array. Okay, now for each I, what we can do is if it is not visited, it means that this component is not being explored until now. So this component, how much it will contribute? The total number of nodes minus 1. And the number of nodes I want to find using a DFS function call, and it would need the supporting of adjacent list and visit array, right? Okay, and finally we can have the answer. Okay, now we have to have the DFS array. Okay, for that DFS would be this. We will have a node, and the next one would be an adjacency list. Okay, so since we need an adjacency list, it will be something like this. And finally, we will have a bool visit array. Okay, if we have already visited this particular node, then we don't need to do anything, right? So we'll just return 0. If not, what we should do, first we have to visit this particular node, and we will keep some temporary count of number of nodes in this connected component as ans. Until now we have found one, which we have taken. Now we have to explore all of its children. Uh, for finding children, we can use ADG of node. Okay, and plus is equal to, we can again do a DFS recursive call with this child as the head. The same supportive functions will go on. Okay, let's run this code for any compilation errors or anything like that. Okay, we didn't keep n's value. Stones dot size. Okay, now it should be okay, right? Yeah, we are running the test cases. Let's submit and check. Okay, we are successfully able to solve this. Thank you.